Okay. Um, okay, thank you so much for joining. So I'm just gonna continue from last time that we talk about the groundwater monitoring system. Okay. So okay, so this is what I introduced last time about the how we try to see the clearer picture of the groundwater and also contamination. Um, the importance of the groundwater monitoring cannot be accomplished without having a right monitoring well. So in this picture, you see so many layers of aquifer. So last time I mentioned that we have at least three aquifers in this system. Okay, so I'm just going to capture that one a little bit, in this lecture. So the first aquifer you can see is the aquifer number one. Oh, okay. Why? Okay. So aquifer one, and the deeper one is the second aquifer, and also we also have the third aquifer. Okay. So the first one I mentioned last time is unconfined aquifer. Why do we know that this one is unconfined? Because that is a shallow one. Actually, shallow, it's the top one. Okay, so it's the most shallowest one. And also we see the water table. The water table is right here. Okay, so whenever that you see the water table, so I'm going to draw the water table line so that you see better. The water table line, which is the red one here, that the unique characteristics of the unconfined aquifer. One of the very good observation in this picture is that the connection between the groundwater water table and the surface water piezometric head. Okay, so you can see that here is the sea or the ocean, right? And you see that this is the sea level. I think you see that this is a sea level. So the water table in red, this one is water table, and the sea level in blue, they are actually connected. Okay, so I would say that this aquifer is what we call a coastal aquifer. I'm not sure some of you already learned about coastal hydrology. I don't know what's the name of the class is, but it's about the coastal, system. I think it's supposed to be taught by Ajahn Anurak or Ajahn Butchawan. I'm not sure, but I don't think it's a required course. But anyway, so whoever that interested in coastal system, so you're supposed to, pay attention to that class. But what I'm saying here is that our groundwater system is also connected to the coastal system as well, like this one. So you see that our water table is actually connected to the sea water level. So they are pretty much the same level, but one of the water table is in the aquifer system, but the sea level is in the coastal system. Okay, so this is the coastal aquifer. One of the main problem of the coastal aquifer is that since the fresh water and the fresh water, which is the groundwater, is connected to the sea water, so our coastal aquifer is always salty. So that means water in this part here, area here, supposed to be the mixture of the fresh water and the seawater. So you see that the seawater is the water in purple pinkish color, but the fresh water is the blue water. So in this area here, so you see the mixture of the blue and the purple. So this is where the water is considered here, the water here. it's not fresh water and it's not seawater because it's a mixture of fresh water and seawater. So we call this area we call blind. Blind, it's the you know, the น้ำกร่อยภาษาไทย so brine or น้ำกร่อย in ภาษาไทย so it's the mixture of fresh water and seawater. It's not that salty compared to seawater, but it's not fresh water. Okay, so it has salty salt chloride, you know, contamination in this area. Okay, so that's one thing. So that's the first aquifer that I'm talking about. So the second aquifer, which is this one here, the second aquifer. The second aquifer is considered leaky aquifer. This is leaky. You see that there's some leak. Okay, so leaky means that although they have the confining layers here, they're not totally confined. So they have some connection between the first layer and the second layer right here. Okay, so your first aquifer and the second aquifer is actually connected through the leakage component. Okay, so the water in aquifer B here is actually not totally confined. If the first aquifer is salty, eventually the aquifer B, which is the second aquifer, is going to become salty eventually. Okay, so you cannot control that because the aquifer A and aquifer B, they are connected. Okay, and the last aquifer, which is the deepest aquifer in this system, is aquifer C. Aquifer C can be considered totally confined because confining layers is actually connected. Okay, you see that the confining layers is on the top right here and also on at the bottom as well. But so the water in aquifer B and aquifer C, they're not going to mix, I think, you know, not at this point when we look at the system here. But last time I already mentioned the unique characteristic of aquifer C as well. I said that if you look at this part, you see that aquifer C is have water table as well. So the water table is right here. So you probably confused like, oh, how come Ajahn said that water table is actually the unique characteristics for the unconfined aquifer? How come aquifer C, which is confined aquifer, has the water table on the left-hand side? So last time I said that this area is what we call recharging area. Okay, so you guys have cell phone, right? So everyone needs to recharge your battery because you use your phone, during the daytime, and during nighttime, so you recharge your phone. So this is the same thing. So recharging area for the groundwater aquifer system actually means that there needs to be the place or the area that the groundwater got refilled. So when you said that this is the recharging area, so it means that when you have rainfall, so your rain is going to fall every place. So the rainfall that fall into this recharging area is going to have infiltration directly into aquifer C. Okay, and also if it goes directly in this area, so it goes into aquifer B. But for the aquifer A, so the rainfall that got into this area can be refilled directly into aquifer A because it's an unconfined aquifer. Okay, so you see what I'm saying. So for this recharging area here, if we consider this is a system of the aquifer system in Bangkok and metropolitan area, recharging area for Bangkok aquifer system is actually not in Bangkok. So it's in Singburi, which is in the northern part of Bangkok. Like last week until last week, I went into the field my site is in Nakhon Sawan. So if you remember Nakhon Sawan is also north of Bangkok. It's considered the upper, central part of Thailand, or sometimes someone call it the lowest northern part of Thailand. So it depends on how you look at Nakhon Sawan. Before we drive to Nakhon Sawan, we have to pass so many provinces. And one of the provinces that we need to pass through before we reach Nakhon Sawan is Singbuli. Okay, so Singbuli is basically just the province that it's full of paddy fields. People are doing a lot of agricultural activities, and mainly they grow lots of rice. So you see that the most popular business in Singbuli is to sell fertilizers to the farmers. Okay, so if you want to become rich, and if in Singbuli, so you need to be a vendor or sell fertilizers, and also insecticides, herbicides, that kind of thing. So because there are a lot of demands, because everyone grows rice. Okay, so you can become very rich selling fertilizers. Okay, so this is the system that I talked about last time. So you see that the system, the aquifer system, is actually very complex. Okay, so you never see this picture until you have enough evidence to support how many layers of the aquifer that you have. All these pictures can be obtained, from what we call geological survey. You need to do an intensive geological survey in order to get this picture. And sometimes we call this one as site characterization. Okay, so you try to characterize your site. So you try to know how many layers in there, and what seems to be the depth of your aquifer. So this type of thing we called site characterization. Okay, so you need to remember this vocabulary, this term, because we're going to use it a lot in the near future. Okay. All right, next. Before we leave this slide, there's one important thing that need to talk. So whenever you know that groundwater can get into underground through the recharging area, as I mentioned, and for the unconfined aquifer, it can be very easily to refill your aquifer. So that's the pathway for water to get into your system. So if you understand this, so you can imply to the next statement that I'm going to say. You will have to understand that the easier that water can get into your aquifer system, it means that the contamination can also get very easily into your system as well, because your contamination originates on the surface. It can have some source here. This can be potential source. Okay, source of contamination. So if your source is at the surface, and there's some rainfall that fall into this area, so it can directly cause contamination through the flow or infiltration of the surface water into your subsurface formation. Okay, the easier that the water gets in there, that means it's also easy for the contamination to occur. Okay, so it one-to-one relationship. If the water can go in easily as well, contamination is also as well. But however, on the opposite way of thinking, if your aquifer system has a very complex recharge area, so that means your groundwater aquifer is quite protected, from the contamination. So contamination cannot occur very easily in that complicated subsurface formation. Okay, so it's a trade-off. So no matter how easy or hard the contamination can get in there, it's always best not to have the contamination at all. Okay, so that's my message here. Okay. Okay, next. That one's already, yeah. And this is the contour. This is the head contour of the groundwater head contour map. So which we're gonna try to construct this type of map by yourself soon. Okay. I'm just gonna go, yeah, and this is also the flow net that I already talked about. Last time I'm not so sure that I mentioned this, but I'm just gonna mention it again. Okay. So this is what we call mud flow. You probably don't know what it is, so I'm gonna explain. Okay, this flow net, actually I'm just gonna say flow net. The flow net that I already explained last time is the system of flow line or streamline. We can call it flow line or streamlines. Okay, you can have more than one flow lines or streamlines. Okay, and it's the network of another. Okay, sorry, I'm just gonna change the color of my pen a little bit. Okay. So another line that crosses the flow lines in the flow net system is equipotential line. Hmm. Okay, hold on, please.
Potential line.
Okay, sorry. Equipotential lines is actually along, I'm already explained this one, but I'm just gonna say it again. Every dot, every point that you are on your streamline, it means that you have same velocity, flow velocity. Same for the equipotential line. Every point on the same equipotential lines, it represents the same equipotential head. Okay. Everyone knows equipotential head in hydraulics, so we use phi. Okay, so what is phi? Equipotential head. Phi is actually pressure head plus elevation head. Okay, so that's equipotential. That is equipotential head. Okay, got it. Okay. So when we are into hydraulics, which is you need to have strong background in that already. So in hydraulics, especially for open channel flow system, everyone knows open channel flow. So if I have a water flowing, this is my canal, the stream or rivers or canals. I'm looking on the long profile, the long cross section, okay, of the flow in stream or river. So this is my water level. So if you have a water flowing like that in open channel flow, open channel flow. Okay. So the what is what did I say? I should sorry, I'm just gonna use a blank space to draw a bigger and better picture. Okay. So now, if I have a flow, just like I mentioned, I'm just gonna draw my river system again. This is a long cross section of my river, and this is the water level. My water flow from left to right. Okay, so you see that equipotential line phi is actually pressure head plus elevation head, right? What is pressure head for the open channel system? So for the open channel system here, if I have a datum line right here, okay, but that's my datum line, that's reference line. So at section 1, water flowing from left to right, so water flowing from 1 to 2, okay? So everyone is familiar with the hydraulics, right? Okay. I am not teaching hydraulics for you. I'm teaching hydraulics for undergrad students. And also I'm teaching hydrology and I'm also teaching groundwater. So I been teaching these 3 classes for many years now. And I know the linkage between hydraulics, hydrology, and also groundwater. So I'm going back and forth. Okay, so I hope that you're okay with that. Okay, so the pressure head is actually we start with the very simple one first. So pressure head is not that simple. So I'm gonna start with the elevation head first, which is the Z. So the Z is the measure from the datum point, the datum line that I use for the datum in this case. So the elevation head is the measure from the datum line to bottom of the channel in cross section 1. Okay, so at the cross section 1 here, this is Z1. Okay, so that is the measurement from the datum line to the bottom of the river. And then for the pressure head for cross section 1 is the measure from the bottom of the channel to the surface, to the water surface. Okay, so that is P1 over gamma. So that's pressure head. It's the same for section 2. Okay, so the measurement from the datum line to bottom of section 2 of the channel in section 2, that is Z2. Okay, and then also the measurement from the bottom of the stream or river to the elevation surface water level, that is P2 over gamma. Okay, what is gamma? Everyone knows gamma. What is gamma? Everyone knows gamma? Should know. Rho is the density, right? Gamma is specific weight. Which is equal to rho times G. Okay. Now you know Z1 and P1 over gamma. You also know Z2 and also P2 over gamma. That's pressure head. So the summation of Z and P over gamma is going to be phi here. You see that. So that's your phi. Okay, so I'm gonna say this. So this distance in green, that is phi1. Okay, and also this distance in green at section 2, that is phi2. Okay, yes. All right, now I'm going to say that the purple line that I'm drawing here right now, that is equipotential line. Potential head equipotential head for open channel flow, okay? Because that's where you measure your equipotential head. You measure phi1 at this point, so this is the equipotential head. And then you measure phi2 here, that is equipotential head. So when you connected this line, so that's the equipotential line for you, okay? And the equipotential line represents the equipotential head, the equipotential head, yeah. All right, okay, you understand now. I'm gonna just get back to our PowerPoint. Okay, so for groundwater, we also have FlowNet. That is the network of streamline. The network of streamline and equipotential line. So it tells you how the groundwater flow, okay, from where to where, and what seems to be the equipotential heads, you know, in the system. So it will flow, you know, from higher equipotential head to a lower equipotential head, okay. Sorry that in this picture, there's no numbers, so you don't see which one's higher and which one's lower. But for the sense, you know, the groundwater is always flow just like surface water, so it flows from the higher equipotential head to the lower equipotential head. Okay, so this picture tells you that. All right. This picture is actually generated from the numerical modeling software, which we named MudFlow. Okay. Okay, so MudFlow is actually the software. It's numerical. It will help you model and program how groundwater flows and moves. Okay, so it's not easy. It's actually very effective. Okay, so we now using MudFlow a lot, you know, for Department of Groundwater Resources, and also I'm doing a lot of you know, research based on MudFlow, and now the current research they're doing is the coupling, you know, MudFlow with other model, so that we can capture you know, the behavior of surface and groundwater dynamic relationship. Okay, so that's how we're doing it, and that's seems to answer the problems, you know, in some during the dry season that people don't have enough surface water to use, so we're relying on groundwater. So we like to know how the surface water and groundwater dynamic interactions in that specific area really is, you know. So that's why we're using the couple model of MudFlow and other surface flow models. Okay, and also we're doing this for you know, some part of the area that we're using nature-based solutions. So we use MudFlow and you know, and also other flow model like SWOT to, you know, clearly identify whether the nature-based solution that we put in that area is really working, and how efficient is the nature-based solution performance. Okay, so this is how I'm using modeling technique, you know, in a combination with other things, you know, to help answer some very difficult questions that from the policy to operation at this point in our country. Okay, so you need to know the name of the model, which is MudFlow. You can search, it's actually USGS. You know, USGS is the agency. It's actually short for United States Geological Survey. So they do a lot of groundwater, you know, business, and also work related to, you know, geology and also water in the United States. I have lots of friends in USGS, and now we still also collaborating. Okay, so I'm not going to talk more about mud flow at this point, but we will touch it after midterm exam. Okay, all right, that one. Okay, so this picture is actually telling you a little bit more detail, continuing from the last slide. This one's also, this one is generated from mudflow. So you see the flow network of the equipotential line and streamlines. Okay. Hold on, please. 1 second. Okay, I'm back. Sorry. So this one is a little bit detailed compared to last slide. Just want to tell you that we can divide our system, flow system, into low flow system. The low flow one, which is local flow, is a low flow. Sorry, local one doesn't really have to be low flow, but always it flows faster. Always faster. So it's why I said it's faster, because it use less time to travel from one point to another point for groundwater in this area. So it has like shorter flow path and also faster flow rate. Okay, faster flow rate. And it only covers a very small area. So just like in here, this one in this local flow region, it only covers a small area or small region. Water flow from one point to another point with a faster flow rate, but covers smaller area, smaller part of the area. And then we also have a bigger flow system, which we called it a sub-regional flow system. The sub-regional is bigger than a local flow system, but it has slower flow velocity. But it's it has like longer flow path, just like I'm drawing now. Okay, so this is longer flow path. It covers larger area, but it's not that large yet compared to the third type of flow region in this picture. So we called it subregional flow system. Okay, so you see that the first one is the local flow system, smaller area, and then we have middle scale flow system. We call it subregional flow system, has a longer flow path and slower flow velocity. And the last one, we called it the regional flow system, the third one. You see that it covers a larger area from one part to another part. It has longer flow path, very, very long flow path, slower velocity as well. Okay. So when we deal with groundwater, so we deal with local flow system, or we're dealing with sub-regional flow system, and we also deal with a regional flow system. Okay, it depends on you identify your studying area, how you identified it. Okay, keep in mind that when we're dealing with modeling, not only groundwater modeling, it can be surface water modeling. The smaller picture, it has like clearer picture of what you are investigating. But the larger of the studying area, just like when you upscale from local to sub-regional, and then from sub-regional to regional, you upscale from smaller system to a medium-sized system and to a larger system. The picture got less clear. Okay, from you move from a small to medium to large, the picture got less clear. Okay, so that means your model needs to be designed to fit properly to the problems that you try to answer. Okay, if you need to answer some problems at a very small scale, it needs to have a lot more detail. So you cannot use a sub-regional flow system. It may not be able to answer what you are looking for. So you have to go with a local flow system, and how local, it's up to your experience and also up to how well you understand your questions. Okay, so if you want to have a bigger picture and you want to answer like a bigger type of problem, you can go to regional flow system for the bigger picture, because you don't need to go into the process based system. You can use a regional flow system. Okay, but it needs to be well designed as well. Okay, so I'm doing at every level now. The one that I'm doing for EEC is the Eastern Economic Corridor in the eastern part of our country. I'm not doing a local flow system. No, I'm not. And I'm not doing a sub-regional. I'm doing a regional flow system because I'm answering at the policy level. I don't need processes. I need the effect impacts at the regional scale. So I'm using regional flow system. So that's appropriate. Okay. But for some of you who wants to explore I don't know, so I don't know, I just don't want to raise example, but for research based, most of the time we need to use the local flow system, because for research you need to look into the process level, so you need to use the local flow system. Okay, all right, next one. Oops. Okay, so this is example of the groundwater monitoring system. Oops, sorry. The groundwater monitoring system that I mentioned last time is what we call the nested well. Okay, nested wells. Sometimes we call cluster well. So it's the same meaning. They have the same meaning, but different, terminologies. Nested means that you have more than one well. Cluster is also, the bundle of many wells together. So the reason behind the necessity to have the nested well or cluster well is because we need to get or take the samples at different levels. Okay, so you can see that our nested well has, in this case, 6 bundle well, and each well has different depth. Okay, they have different depth. The reason that they have different depth because you designed it. You designed the specific depth for each well in order to take samples from that specific depth. Okay, so in this case, you see that our well has a opening here, and your deepest one has opening here. So during the opening means that you will get water flow into your well from this opening screen. Okay, so you will not get the water from other depth or other location at all. You need to get the water from the opening that you have in each well. Okay, so you see the arrows that I draw in this picture that represents the water in that region is going to flow into your well. Okay, so it means that for the well number 1, so you get the water flowing in from the shallowest depth. Okay, and for well number 6 on the right hand side, so you take sample from the deepest depth in this region from these nested wells. Okay, so you take sample from different depth, and at each different depth, it could means different aquifers. For sure, in this case, you have clay layers. Look at the system here. So you have clay layers here. That's one confining layers. And then you also have another clay layer here. That's the second confining layers. So in this picture, I would say that we have 3 aquifer. So this is aquifer 1, this is aquifer 2, and this is aquifer 3. Okay, because they have 2 confining layers separate them out. So you have 3 aquifers. So you need to have the monitoring well that covers all those 3 aquifers. So I would say that well number 1 is actually taking care of the aquifer 1. Okay, and well number 2, 3, 4, 2, 3, 4 is covering the second aquifer. Okay, and last but not least, which is the well 5 and well 6, those have opening in the third aquifer. So this one is taking sample from the third aquifer. You see that well number 5 is actually here. It actually has opening in the clay layer. I'm gonna say that the reasons behind this probably consists of 2 reasons. First one is that they want to see whether you have a leaky aquifer system or not, so that they take samples from the clay the depth that seems to be the clay layers. Okay, so if you can take some water from that clay layers, that means that your clay is actually transmitting some water. And the second reason that why they have the opening in the clay layer is probably some uncertainty. So you see that your clay, it doesn't really have the how could I say, the uniform thickness. It has some thinner layers and also thicker layers. So when you install the well, sometimes your opening did not really consistent with the aquifer layer. So that's possible. Okay, could be some uncertainties, could be some heterogeneity, in your system. Okay, all right. Okay. Okay. So since this nested aquifer, nested monitoring well, nested wells did not really reach the same aquifer. So what you expecting in each piezometric well must be different. What I'm saying is that the piezometric head in each aquifer is not supposed to be the same. Okay, so remember that I said we seem to have three aquifer system, 1, 2, and 3. Okay, so well number 1 takes, is actually enter into the aquifer 1. So the piezometric head that you read from well number 1 could be somewhere here. For well number 3, for well number 6, that it takes samples from aquifer 3, which is a confined aquifer. So you probably have higher equipotential head. Okay, so you probably see the water level in aquifer from aquifer C in monitoring well 6 have higher head compared to monitoring well 1, because monitoring well 1 represents the monitoring well that associated with aquifer 1, which is unconfined aquifer. So it has less pressure. So you probably see the higher equipotential head in well number 6 compared to number 1. This is just my analysis, okay? So, but you need to understand that the equipotential head, from different aquifers probably not the same, okay? And for well 2, 3, and 4, they're from the same depth. So they probably have pretty consistent head piezometric head in those 3 wells. Okay, I'm just gonna change my drawing a little bit. Okay, and for 5 and 6, pretty much the same. Sometimes you get a really high pressure in the confined aquifer, and it has higher equipotential head compared to the unconfined aquifer. Okay, done. Next. Okay, this is how. Just going to drink some water. Just 1 sec. Okay. In this picture, I'm demonstrating how we take samples, okay, from groundwater. Some of you may not have a chance to see this kind of pictures before, because it's actually not the same for groundwater and surface water. Okay. So one thing that now you understand is that we do monitoring through observation wells or monitoring wells. Okay. So we need to dig very deep into the underground in order to reach the specific depth that you like. And then you just stabilize your wells and start to take samples. Okay. This is the first picture here. You see that it's the first it's very, how could I say, it's very primitive step. Primitive means that you don't need to wait until your wells are well constructed. You don't need to wait for your wells to be completely constructed before you start to get or take samples. You can take samples right away. You can see in this picture that your well looks very primitive. Still don't have, the concrete setting or the fence or anything like that. Once you're done with digging the wells and the wells stabilized enough, you need to wait a little bit, probably 3 days after your well is constructed. The reason that we wait 3 days waiting, okay, is that because once you done with your well construction, you dig the wells using the machine and using a very highly efficient machine. It got lots of soil, it got soils and dust and rocks and so many things in your water. Okay, so your water got disturbed. So what happened after you're done with the well construction is that the groundwater in your well is always very turbid. Okay, water is turbid. คุณบีคุณรู้จักคำว่า turbid ไหม You know the meaning of turbid? No, it means ขุ่น It's turbid means it's the opposite of clear. So it means not clear. The water is not clear, the water is turbid. Okay. So once you're done with your well construction, you got lots of soil and rocks, in your water. So the water is turbid. It's not clear yet. So you wait 3 days, approximately sometimes around 3 days until the soil, rocks and dust, they got precipitated down. So you get a clearer picture, the clearer water. Now you can start taking samples. Okay. So this is the equipment that we use to take samples from our groundwater. So one of the I'm sorry, let me rephrase it. This is one of the instruments that we use to take samples from the groundwater wells. I will show you more pictures later. You can use this, what we call this is baler. That one of the equipment that we use to take samples from our groundwater. So it's like a kind of cylinder. It's like a long cylinder like that. And then you just attach your baler with the rope here. I said rope, but it could be cable. In the past, when we're not dealing with a lot of very deep sample collection, so we can just use rope. But when we deal with a very deep, down to take samples, it's rope is not strong enough. Okay, so we need to replace it with the cable. Okay, so cable is stronger and it prevents the accident from we lose the samples because our rope gets kind of cut, or maybe it cannot hold the weight. So our rope got broken. So we replaced with cable. So you just use rope or cable and then lower down your baler into the groundwater well. And then when it reach the specific depth that you like to take samples, so you just open the baler. The baler has a mechanism that when you how could I say กระตุกภาษาไทยภาษาอังกฤษคืออะไรวะ when we อืม when we strike the rope one time, our baler is going to open up, and then water flow into our baler at that specific depth that you want to take samples. And once it's done, so you just strike your rope one more time, okay, and then it close. Your baler is closed, and then you just take the baler up to the surface. Okay, that's how we take groundwater samples using the baler in the first picture. All right. So in this case, he said that it's 60-meter deep groundwater sampling. So that's not too deep. You can use rope, but for more than 30-meter sampling depth, I always use cable. I don't just relying on the rope anymore. Okay, but in this case, they use rope for the 60-meter deep groundwater well sample collection. Okay. And this is and then we use so many groundwater probe just to measure the water quality. This one you can see that we use electrical conductivity probes. Okay. So this is the probe. It looks just like a pen, but we call probe. So you just dip your probe into the water that you like to take, electrical conductivity measurement, and then you can read the numbers from the screen. So it's very easy these days, to just measure the water quality on site because you have the probes that can measure many parameters. And maybe you have questions. Ajahn, why is he measuring the groundwater? But it looks like this is the surface water, isn't it? It's on the ground. So I would say that they call this one as seepage water. So they know that this is the seepage water from underground. So this is considered groundwater. So they want to measure the quality of the groundwater that seep out from the aquifer, and now it's seep out to the surface water. So they take samples at this point and measure the electrical conductivity. Okay. Another type of groundwater samples is we use the pump to pump the water from deep underground to surface like this one. So this is where the groundwater well that dig into underground, and then you don't lower your baler into the well like that, but now you pump the water from the well out to the surface. So you have groundwater flow out like this, and once the groundwater flow out to the surface, and then you just start collecting. You start collecting the water. This is water flowing out, and these are groundwater. Okay, because you pump the water from underground, so groundwater, and you take samples from this water. Okay, you can take measurement like this, here. So you get the your chemical parameters of the groundwater at this specific location right away. Okay, you don't need to take it back to the lab because you have the on-site electrical conductivity and other type of parameters measurement. Okay, and but you need to collect your data to analyze some specific property at the water lab as well. So these are the it's the water sample bottle. Okay, so you take samples and put the sample in your bottles Usually we use different type of bottles for water collections. It depends on the parameters that we're measuring. Okay, you can use the plastic bottles, you can use glass bottles, but we have protocols that you need to follow in order to preserve your samples, and you need to send all these samples back to the lab within 24 hours after sample collections. So it's quite difficult to do the sample collections, and also for the groundwater monitoring system in a very remote area, because in a remote area it's hard to ship our samples back to the lab within 24 hours. So we need to be very careful, and we need to well plan for groundwater water collections in a remote area. So I'm just giving you examples of how we collect samples for groundwater monitoring. Okay. Next one. This is how it looks like, the equipments that we use in the field for groundwater sampling and analysis on site, and also water collections, and take the samples back to the lab. We always need to have GPS, okay? We always have field book, just to write down, whatever that we observe in the field. This is very simple for geological survey like us, we always have field book. And we also have water bottles for the samples that we like to collect and, send back to further analysis in the lab. You see this word acidified and non-acidified. So when we need to preserve our samples, so you always fix it with acidic solution. เราจะต้องหยดกรดลงไปนะคะ so we need to fill our samples with some acidic solution to preserve the samples before we send them back to the lab. So we always have acidic solution with us, and do the sample preservations. We also need to have syringe, those is very important for taking samples and filling up a small water sample bottle like that. Okay, we have EC, electrical conductivity meter, we have pH meter, and we also have alkalinity set to measure the pH of our groundwater samples. So this is the necessary tools that we need to have in the field. This is a general parameters that we measure for the groundwater. For just general or basic groundwater observations or groundwater monitoring. But if you need to observe or monitor specific contaminants, so these parameters are not enough. Okay, so we need to have more parameters add into the the parameters that we collected. Okay, but this is just for the basic and simple. So what are we measuring? So we measure electrical conductivity, we measure the pH, and we measure the temperature of the groundwater samples. And we also analyze for cation. And this one, I think you already know, cation means positive ions. Okay, and anion is negative ions. Okay, so the positive ions that we measure and analyze is like calcium 2 plus, magnesium, sodium, potassium. And for the anion, so we measure the alkalinity, which is the HCO3. And we also measure the chloride ion. We also measure the sulfate ion, also nitrate. Okay, and some other biological parameters as well this day, biological parameters. Okay, for example, total coliform bacteria is one of the biological parameters that we're measuring. We call it TCB. Okay, so this is just example. I'm giving you example. And other biological parameters that we're measuring is fecal coliform bacteria. And in short is FCB. Okay, These are the biological parameters that we're measuring. In the past, we don't really measure biological parameters because of the budget. And also the very delicate sample handling. So we need an expert, to do water collection for biological parameters as well. In the past, we don't do that very often. It's quite time and money intensive. Okay, so if we don't have enough budget, so we don't usually analyze for biological parameters. Okay, but that's one of the weak spot, because there's some in the past recently I have involved in water quality analysis for so many organization and agencies, and for groundwater I redesign the parameters that they need to concern about. And at the time that we try to come up with the parameters that we need to analyze, they always don't have those biological parameters included into the work. And then I try to add the biological parameters. And at the time that we are arguing whether we should include the biological parameters or not, the reasons that they gave to me is that we never take samples and analyze for biological parameters before. We don't think that our groundwater is that dirty, and we don't think that there will be any bacteria, especially for the coliform bacteria and fecal coliform bacteria in the groundwater system, because the groundwater they still believe that the groundwater is supposed to be very clean, okay, because they pass through so many layers of porous media, sand, and rocks. So they think that the quality of the groundwater is supposed to be very good, strong, and a very clean and clear. But I finally won, and I said, okay, let's try to monitor these biological parameters for a couple samples, and I'll show you the results. And if your preliminary samples and analysis showed that no total coliform bacteria or fecal coliform bacteria at all, so we'll stop analyze for biological parameters. We just only analyze for other chemical and physical parameters, and they okay. And after my first round of results came out, and we found that 100% of the samples that we collect from the groundwater in that study area are actually contaminated with total coliform bacteria and also fecal coliform bacteria. It's not just slightly contaminated, but it's heavily contaminated with total coliform bacteria and the fecal coliform bacteria. So they were so surprised to see the results like that. And I said that I'm not surprised because groundwater is not that clean. And second thing is that the groundwater that we took, especially from the unconfined aquifer system, always contaminated with the bacteria, because the unconfined aquifer is actually connected directly to the surface water. And if you have any human activities on the surface, like, if that area has like school and domestic communities, so you will always find the the bacteria from sewage system that leak into your groundwater. So from that on, we collect samples and always analyze for biological parameters. So they started to believe me, and then we changed the context of groundwater sampling and analysis from that point beyond. Okay, so I hope that you see the importance of groundwater monitoring. You see that groundwater monitoring is basically not how can I say, you need to custom design to fit your specific objective. You cannot just have one basic monitoring system. You need to design to fit the nature of your site. You need to design to fit the objective of monitoring program. Okay, It's up to like if you want to and you can have basic package of monitoring, but that's not going to cover all you need. You need to think what else that seems to be important and you left out. For example, the biological parameters that I'm mentioning. But for the basic analysis for the parameters, you can always go with these parameters like electrical conductivity, pH, temperature, cations, and anions. So those are basic package for the monitoring. Okay. So don't believe that your groundwater is clean because it's not. Okay. And once you see that human activities are actually directly related to groundwater quality and especially for the biological parameters, so you start to see the importance of monitoring to include the biological parameters analysis as well. Okay. And we have tools these days to help you understand more of the groundwater and also monitor for your groundwater, but you need to be smart and detailed enough, to design your monitoring system to fit and to be able to achieve your ultimate needs and also to answer the questions you have. Okay, so that requires brains and require experience. It's not easy. Okay, so I'm just gonna stop here, and next time we're gonna continue to talk about the groundwater pollution and also different types of pollutions and also case studies that I have experienced and also get involved since the beginning of my career after the PhD. So I'm just going to talk about the groundwater pollutants and case studies next time. Okay. I'm not so sure yet next time is it going to be online on site. I'm just going to let you know beforehand, okay, so that you can prepare, but I don't know because it's up to my schedule next week and I don't know yet. There's some unconfirmed activities. It could be online on site. I'll let you know. All right. Okay, great. Thank you so much. And I will send in this video clip so that you have the clip to study as needed. Okay. Thank you so much for joining and I'll see you later. Thank you. Thank you.
Thank you again.
Thank you again.